Alrighty. We're back with the our session of number systems representation. There you go. Decimal system, the number decimal system or numerical system base 10 can build numbers using the digits 0 to 9. If you want a larger number such as 10, you will have to put together the digit 1 and 0, and then or 11 you put two ones together and so on, right? So it's a combination now. Binary similarly uses 0 to 1, so let's put that in brackets so it's an interval. So you can build numbers only mixing the digits. If you want larger numbers than 1 or 2, then you have to put other more digits together, correct? Just like in the decimal. Octal would be the same in the way you form numbers, but the number of digits available is just from 0 to 7. That means you will end up having numbers such as 50. This is not the number 50, it's the base 8 and 77, for instance, or a larger number would be 577 and so on. Hexadecimal, we said the hexadecimal system use numbers between 1 and 15, but as I explained it earlier in a different session, numbers between 10 and 15 inclusive, 10 and 15 are represented by letters of the alphabet. So if I use the letter A, it means 10. If I use the letter F, it means 15. If I use the letter 1F, it means a larger number than 16 for sure. In that case, if I use 1 and 0, this would mean 16, correct? Because it's a number that is 1. It's now the smallest number greater than any number that can be represented by just one digit. Make sense? Alright, so how do we transform from binary to octal? So what we want is the octal system. What you could do is seeing any number in binary, such as 1010, just like the one we've been working on. And this is base 2. You want to transform into a number that is base 8. So the straightforward, and this method has to be, you need to learn this method, is to take groups of 3 digits in this number. That is, if you have this number on the left, right here, then you will do is take groups of 3 starting from the right. So I would take 0, 1, 0. That would be the first group. The next group would be a number that looked like this, but this number is just 4 digits, so for completeness you could just add 2 zeros. That would be your second group. Now this is sort of the octal number, but what you want is something that resembles numbers between 0 and 7. So you need those digits, those groups, right, to resemble the digits within the octal system. So what you do is use the polynomial that we used for transforming any system into decimal to turn those, to map those digits in binary into octal. Well, how we go by doing that? Well, we learned that we can use based, this is base 2 now, right? So we went to, this is still base 2, but now we're forming those digits. So this digit, it's pretty much the polynomial that looks like this, right? 2 times 1, and I guess I'm just going over 2 times 0. This would be the exponent 0, 1, and 2. Based on our previous knowledge of how we go by adding these, the only number and the only term that remains in this polynomial it's 1. It's 2. Right. So what about this guy here? Well, this guy here is just 0 times 2 to the 2 plus 0 times 2 to the 1 plus 1 times 2 to the 0. And this number is just 1. So if you just put them together, this number is an octal number. So 12 is your octal value. Now, if you want to go back, let's say you have a number such as 1 and 2 in octal, and you want to transform it into binary, right? So this is going to octal, this is going to binary. You will perform a similar operation. You will do is, what you would do is take 2 and 1, right, and use the polynomial to transform them back. So you want to say, okay, what number can I use to turn this into binary, correct? So you could use the small table that we used earlier, right? So let's see. Not the table, just converting 2 as if it were just the polynomial kind of thing. So let's see if that makes sense. Let's see, first place the number 2. Let's start doing the number 2 here, and you need to get used to the polynomial that we've been working on, and sort of like learning that every time you, if you had a number, let's put an example, if you had a number that it's binary and you have only ones, okay, if you were to transform this into decimal, each position is worth, the first one is worth, let's say 2 to the 0 times 1 plus, let's see, let's put the whole thing together. Times 1 plus 2, right, all together. So observe this pattern. The first term is 1, the next element is 2, then we have 4, then we have 8. So you sort of kind of speculate what's the next term. It would be the power of 2 of 8. So it's just adding new powers to that number. So this would be 8 to the 2 would be, let's see, that's so I think, no, it's 2, right? You're sort of like multiplying by 2 each time, right? 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8, and it grows, right? It's sort of like a pattern. Now, if some of these elements are not ones but zeros, well, each term it's gone, correct? So you have to make a polynomial so that adding numbers in groups of 3 gives you 2. So you can now say that, let's say, let's go down here because now we have this. So what combination, what sort of terms in this polynomial add up to 2? Well, just this element, right? That would be this guy. So by elimination, you would say, well, this number, these digits, in groups of 3, if I take these 3 together, this guy here and this guy here must be 0. In order to make them 0, instead, those digits have to be 0. So taking a group of 3, I made the first term 0, the second term 1, and the third one 0. Because I know this number binary turn into decimal is 2. And what about the other term, which is 1? Well, I need a group of 3 digits, and if you observe again this polynomial, what gives you 1? Well, just because now we're taking in terms only in groups of 3 of this polynomial is starting from right to left, again, for any digit that we want to convert from octal to binary. So in this case, these two, we have to make them 0, and we should keep the number 1. So that gives us the combination of digits that are 0, 0, 1. Correct? So that is the conversion, and that is, so the result of this is just this lengthy number. And just like any other system, zeros on the left after a 1, if there's no other 1, they don't have a value, they are not worth anything. So that would be your number. Alright, that's just the next conversion from octal to binary. In a similar fashion, let's see, if you want to transform, let's think about this. You have to reason through the following example. So this is hexadecimal. So if I give you a number in hexadecimal, such as A, letter A, then this is hexadecimal, and you want to transform it into binary, right? First of all, you have to figure out what you need to know that this letter is called a nibble. Okay, it's spelled nibble. If you want a binary, you want to just transform this into a group of 4 digits. All right, 4 digits. That's what you need to represent. That's the minimum number of digits to represent a letter, which is a value 10. So let's go here, and this is just the value 10, correct, in decimal. Let's see, is that correct? Just it's a still, it's a two-step process, right? It's turn it into 10, and now you know that. Let's do that, and 10. So we're moving towards the whole process is going to 10. And then 10 requires 4 digits. And as we learned before, the first, if you want elements in binary so that some of the terms in the polynomial remain, then you will keep those that are words. So this digit is word 1, this is 2, this is 4, and this is 8. So which one of these digits or bits, this is the unit of binary, the digit is called a bit, should be on or be 1 in order to add up to 10? Well, it should be clear. This should be 1, should be 0, this should be 1, this should be 0. That is because 1 times 2 to the power of 3 is 8, so that's 1, then 1. The next term should be 0, then the next term that should remain should be at 2. So 8 and 2 will survive the elimination. So there, this number is the representation of letter A in binary. Again, if you had FA, then you will take groups of 4, 2 groups of 4, right? Something on those lines, right? And transform 10, and F is 15, and then you need to figure out 15 would be a number that looks like 8 and 14 is 12, so we're behind, we're a little bit low, so you would need all those digits to be 1, so that 8 plus 4 plus 2 plus 1 end up to be 15. And A, we already figured out it was this guy. All right, so all together form the binary representation. All right, hopefully this video was useful. Thank you for listening.